all do we have in the chat today? Let's see. It is the start of office hours. Had a contact appointment this morning, so sorry about the late start right there. Got Mubot over here. Lane, good to see you there. Awesome. I think you messaged on the Discord, did you? Yes. Thank you for messaging. Feel free. That's the easiest way to contact at any time and say, hey, when's this going on? Yeah. Which problems you working on? Let's throw out some points for you being here. What are you working on? What do you want to do? You name it, we do it. Let's go up here. Let's load up my Pearson. And loading up my Pearson as we speak. My Pearson's getting loaded up. That's what Lane's saying over here. Whatever you want to work on, Lane, let us know. We'll take a look. Quiz 5, part 1 mostly? Yeah. Tell me which questions you're working on the quiz, and we could do those. Because it cycles through a whole bunch of different questions. Let's see here. Assignment manager. We could try to do just as many as we can, because we got a good bit of time right now. There's a lot of Chapter 5, Part 1 questions. And I really like this part. It uses the empirical rule, and a lot of these you can solve kind of in your head. It's kind of fun. So, let's see right here. Let's see here. Let's get the notes up for the thing. We got this right here. Edit the video. There we go. And let's start right here with Chapter 5. Statute 1. Chapter 5. Quiz 1. The average score. Lots of great questions here. Let's go do it. Okay, so for the first one right here, you'll notice that it talks about the average score on a midterm was 75. So and the standard deviation was 7. What does the average tell us? Like, we need to think about what we're drawing right here. We need to think about what we have with this and what it's showing to us. If the average is a 75, what does that tell us? I know this is an easier question, but if the average is a 75, that is the what of the distribution. Think of a C word. If the average is a 75, because the more we understand this, the better we can do these problems. And it said this right here. Easy question, but we need to understand all the parts of it. Because remember how we have shape, center, and we have spread. So I got to give a shout out to Adam Spanbauer right here, who made some really amazing apps. And you can really see the shape, center, spread looking at these apps. So if you haven't pinned this right here or take this, I'm going to pin it in the chat. But this is going to help out with a lot of the problems right here for especially Chapter 5, Part 2. So if you look down here at the bottom of the curve, you can see this has a center of 0. Now watch the center right there. I can just move it and move the center. The shape is normal. So hey, Caitlin, good to see you here. So it's a normal shape. It has a center of 36 right now. We'll put that to 75. Now it has a center of 75. And then this controls the spread of it. If you notice, the number line is getting wider. So the standard deviation is the spread, and instead it has standard deviation of 7. Now, we're not going to be able to perfectly answer it from the graphic below because it doesn't exactly show each standard deviation. But going down here, we can draw each standard deviation on the curve ourselves by going right here, putting each standard deviation. Now, what I like to do is I always put the z-scores below it. And this is how to get the problems right and to understand the concepts that z-scores are always the standardized metric for how many standard deviations something is above or below the mean. Now we put the context below the curve, and the context tells you what somebody scored, where a score of 96 is 3 standard deviations above the mean of 75, where a score of 68 is 1 standard deviation below, and so on. We go down to 61, and we go to 54. 54, yep, that'd be right there. A double thing, yes. So double check your numbers, make sure they're correct. Now, this is the deeper understanding of the problem that we want because it's not that complex of a problem right here. It just says you have a z-score of -2. What does a z-score of -2 tell us? So what does the z-score of -2 mean? It always has the same meaning because z-scores are standardized units. So what does a z-score mean? Like, that's something we should be able to tell someone, like, oh, a z-score tells you this. It's how many what's someone is what to wear. So we should always be able to tell someone what a z-score means. So I'll let people think about it, or but have it written down. If you 2 standard deviations below. Exactly, Lane, exactly. So we know the person is 2 standard deviations below the mean. So you could just go to the mean, which we kind of already have drawn out, and go 75 minus 1 standard deviation minus another standard deviation. And once again, we already drew this out, and we could see that 2 standard deviations below the mean is 61. And this drawing right here is going to be the big help on solving it, or just making sure we get a lot of problems right. That is an easier problem. Which ones are you working on, Lane? Let me know. I'm just going to keep going through here, and we'll just do them in order. There we got people with a z-score. So if you name one, Lane, give me the first few words of it. I'm going to start putting in the problems as we do them, and just name a problem. Once again, we're going for the deeper understanding on these problems because we are solving them, so we got to make sure we understand them at a higher level, not just the answers. So getting the answers is one thing, knowing how to solve it is another. So this one is kind of a similar problem right here to the last one where it says people with a z-score. So what does the z-score tell us? How many standard deviations someone is above or below the mean. A company that manufactures, you got it. I think it's the rivets one, right? We'll do that one next, Lane. You got it. We'll find that right after this one. So they are telling us someone's z-score. So if, and this is where you want to get with z-scores. If I told you, think about this. So Lane, I think you got it. Like, I think you have the deeper understanding we want. If I told you the z-score on the test, your z-score was 2.5. Let's just go 2.5. What would you want to know then? If you wanted to know what you scored, what would I have to tell you? So if I told you your z-score was 2.5, what information would you need? Because the z-score, once again, the definition is, go here to the definition. Z-score is how many standard deviations someone is above or below the mean. So you'd need to know the mean. You need to know the mean because if you want to know what you scored, you're going to have to know the mean. It's one thing. And then you'd also have to know the what. So if I tell you the mean was 70, so your z-score was 2.5, and the mean of the distribution was 70. That's mu right there. We'll do some IQ tests. You got it, Kaylin. That is. What else would you need to know your score? Like, well, Brian, what did I score? And you're like, oh, well, a z-score of 2.5. So, I think, is that there's a really tough one on one of these. And the standard deviation. So because you know you're 2.5 above the mean, but, well, what's the standard deviation? Well, think about this. If the standard deviation is 4, so let's do 2 scenarios. Like, let's say the standard deviation up here, let's say it's equal to 4. What did you score? Just hypothetical. And so what you'd want to do is you could draw your little curve. And on the curve, you'd put 70, and then you go up, and you're right here at 2.5 standard deviations above the mean. It can always be drawn that way. But the standard deviation is going to determine the length of units here. So visually, you might be able to figure it out pretty quickly. Now, the mathematics for it is that the observation equals the mean plus the z-score times the standard deviation. But that's literally how many standard deviations are you above or below the mean. So what did you score if your z-score is 2.5 right here? If you can come up with problems like this, you're doing really well. If you can think about this. And 80 exactly, because if we plug in the numbers right here, we have 74, 78, and you can see 82. You can plug in the numbers here that 80 is equal to 70 plus 2.5 times 4. And then we could change this right here to a different spread of 10. And you'll notice the spread right here is going to make this distribution wider. And so, Lane, what is the answer here? And then we're doing your problem next. Now you scored a what if the standard deviation is 10, which makes the distribution spread out more. Remember, shape, center, spread we're talking about here. Happy Valentine's Day, Colin. Good to see you here. Happy from Disney. Love that. 50 points in the chat. So now what did you score? Now you scored a what? We're just changing the problem so we understand how to like solve other versions. 95. You got it. You know how to do this. So the same theory applies right here where this person is 2.75 standard deviations above the mean. So we go here, we plug 2.75 in. We times that by 8 because that's the standard deviation. We add that to 100. And once you add it to 100, it's 122. And that's the answer right there. Good question. Just understanding it. And once again, we want to understand how to draw these curves. and what these equations mean, because this equation right here, although you might think, do I need to memorize that? It's just the idea of that we can find the observation if we know the z-score, because the z-score tells us how many standard deviations something is above or below the mean. If it's negative, it'll subtract from the mean. So it's not so much about memorizing it, it's about knowing the context of it. Let's go find that, was it rivets or something? The question was a company that manufactures. Yes, I think it's rivets. A company that manufactures. And tell me if there's like another version of it. A company that manufactures. Okay. Favorite music. I listen to this song every day. A company that manufactures. Where is it? Ah, it's literally the last one. Wow.
Wow.
Okay. Literally, and Caitlin, if you saw the other question, tell me the number. You might not have saw it, but chapter 5, quiz 1. Okay, let's do it. Company manufactures rivets. Here we go. So they're manufacturing rivets, and it is normally distributed. This is the notation we use to say normally distributed with a mean and standard deviation. Once again, we put the mean at the center, and then the spread is going to be how many units we go up and down each time. So do note that this number right here denotes the distance away we go from the mean each time for one standard deviation. And this number right here is the center of the curve where the z-score would be 0. Always draw this curve right here to help you out. We'll probably take a picture of this and add the z-scores below it. So if you look, we have the proper mean and the standard deviation here. It looks like it's B, because that's too big of, yeah, it's B. It is B. Okay, because this has too big of a standard deviation. 60 should go 60. There we go. And this has too small. That's 30. And that's way too small. That's not 60. That's 6. So actually, they've changed this problem, and they've changed the drawing on it, because they used to have it drawn differently with 2 standard deviations. I bet people complained. Okay, so what do we always add to a curve to help us with solving problems? What do we always add to a curve? So someone put it in the chat. What do we always add? It's number 7 for you. Then it should be towards the end for me, because it does them in order. What do we always add below a curve? So you want to draw these out. If you have a pen like I can draw on your screen, that's really good. Or if you have a sheet of paper next to you, draw it out. But this is the real practice. Every time we always add the what's, because that's always going to be the same standardized units. Below our curve, we will always add the what's below it. The z-scores. Great job. Points in the chat. Thank you, Caitlin, for being here too. Those are the z-scores, and this is going to help us out a lot. We also have some of our drawings from over here. This is a drawing. If you're not in our class, take a picture of it. It can be a huge help. We also talked yesterday during lecture, so I'm going to leave the screen. That's a huge help drawing right there. But during lecture, we also went through and broke down every portion of the curve and found those numbers too. Here's one drawing from class where we went through and did the percentages above or below. And then another drawing right here where we did the percentiles from different classes, talking about the percentiles, and each of the percentiles are marked on the curve. All of these numbers can be found using the 68, 95, 99.7 rule. And so this curve right here is super helpful for that. What percent? Nice job. Right? Yep, Lane, that is correct. 100 points, Lane, helping out. That is correct. Right here, that is what Caitlin's wondering about, between a z-score of 1 and 2. And that is the answer, Lane. That is correct. 13.5. Good work. Nice job helping a classmate like that. That is the percent of area, because it's, if you subtract off the 2.5 above here, if you do it in more of a classical way, 2.5 is above here because 95 is within here and here. And you would subtract off from the 16% right here, leaving the remainder 13.5. So that is how you do it. And Jamarcus, good to see you here. But all of those numbers on the curve right here can be found. And you don't get this on the test, but any of these numbers can be found. Usually we're a little bit nicer. There are some tough questions, but some of them are not as crazy with what you have to find. Okay, would it be safe to say, okay, what is the z-score of 740? Let's first look at 740. And what is the z-score of 740? Very easy to see on this graph. What is the z-score of 740? These are rivets. We want them to be strong and have a strength that is high. So what is the z-score of 740? Those rivets are -1, right? So they're 1 standard deviation below the mean. And so that means 32% is on the outside. Now, how am I getting 32% on the outside? Someone's probably wondering, how in the world are you getting 32%? How in the world is that 32%? Why is it 32%? These are the things you should be able to find on your own right there. So why is it from 68, right? So the remainder on the outside. Because if 68% is inside, then outside total is 32%. So one of these arrows is half of that. So we divide this in half, and you would get here 16%. And that's what you get. And you can check your work, because if you draw the numbers, they should add up to 100. So we would have right there 16 on either side. So obviously, we're just going to look for the answer there that shows 16%. No, because about 16% of the company's rivets have a shear strength less than this, and that's perfectly in line with what we drew right here, showing that right there, if we were to put a mark on the curve, about 16% of rivets have a shear strength less than this. So there's the 740, and there is below it is 16%. So that's not good. 16% of our rivets wouldn't meet the standard. About what percent of rivets fall below 920? So we need to go to where 920 is out on the curve. 920 is at a z-score of 2. Does anyone know the answer to this? See if you can get it in the chat. I'm going to give 30 seconds right here, a little bit. I'll start drawing it out for you. What is below here? Yeah, Lane, you're getting it. Nice job. So the reason being, and Lane is exactly right, 95% inside, leaving, if 95% is inside, 100 minus 95 is equal to 5% outside. That's how we're getting the outside. 5% divided by 2 is equal to 2.5. 2.5 is above here, and then you could do 97.5 is below here. By just going across these arrows right here, you could find it by just going like that and adding up the values. So 97.5 is the right answer. That is the amount below that point. Good work. Questions like that on the test tell you to use the empirical rule, so make sure to do it. Rivets are varying. Okay. What is this one asking about? What is the maximum shear strength for which you feel comfortable allowing the company to approve? Explain your reasoning. Select the choice below. To make sure nearly every rivet are strong enough, the maximum shear strength should be... Okay, they're going for 6 standard deviations above the mean. Oh, wait. Rivets are used in a variety of applications with varying shear strengths. What is the maximum shear strength for which you would feel comfortable approving the company's rivets? Explain your reasoning. Select the correct choice below. A very small probability of failure is desired. Less than 1 out of a million, 6 standard deviations above the mean. The maximum shear strength should be... Make sure that all this is strong enough. The maximum shear strength should be at least... Okay, so I really don't like how they're doing this because they're going to like a 6 sigma process. Yeah, so you'll get to see the answer here. So it's also a little bit weird on how they're asking this. What is the maximum shear strength for which you feel comfortable approving this company's rivets? The way they're asking it, the way it's just a very oddly... The question's great up until this point. It's really just asking you, would you go 6 or 3 standard deviations? The first one probably failure is desired, less than 1 out of a million. The maximum shear strength. Okay, wait. Okay. So I think here's the thing. The way it's being asked is... Our rivets can handle up to a certain amount. Does that make sense? Like, we are saying these rivets are cleared to handle this amount. Does that make sense, Lane? Like, we're saying maybe because the rivet's like on a bridge or something holding it together, and we're saying it's cleared to handle this much force. Does that make sense? Like, we're clearing it to say it can handle this much force. It has this much strength. Like, if you don't exceed this, you're good. Does that make sense? Okay. So with that in mind, we're saying... Here's what we expect from our rivets, that a very small portion won't be able to handle 620. Like, this is when the rivet snaps. The average rivet snaps around 800. So would you want to give a shear strength up here on the right side that we would clear it for, or shear strength down on the low side we would clear it for? Right, left or right side? because we're going to clear it for these rivets. We're going to clear it for these rivets. We're going to say it's good to be used at this shear strength. Would you clear our rivets on the left side of the curve or the right side of the curve? Because our rivets on average break about 800. So where would you clear it? See, that's the trick to it. And I think I'm right. Is we would clear it on the left side because our rivets on average snap around 800. So when we go to the consumer and the consumer says, my bridge needs, like what if the consumer said, my bridge needs a shear strength of 920? What is the probability the shear would snap or the rivet would snap? Over here, there's a very high probability of failure. Everything down here is failure. Because if they need 920, well, but here's the thing though, is we're clearing them to say, if someone comes to us and says, I need a strength of 920. I hope I'm doing this question right because they added this part. I think last semester they did. If someone says, I need a strength of 920, then we'd say our rivets probably won't work for you. Does that make sense? We would, or widgets or whatever they're called. We would say our widgets don't work because they're on average set for about 800. If you need 920, we can't promise you it has the strength necessary. Does that make sense? They need a strength of 920, and it's very likely our rivet won't do that. Does that make sense? This is more of like a manufacturing thing right here. Because they say, I need it to work at 920, and we say, it's probably going to break because most of ours break around 800. But what if someone said, I need a rivet, and we're going to go 6 standard deviations below the mean. So is the weight in the graph the weight they can support? Yes. This is like their strength to which they can withstand. So anything like, let's say over here, someone comes to me and says, I need something, we'll go 6 standard deviations below the mean. And that's 360. So now they say, I need 440. Do you think our rivets can handle 440? Do you think our rivets can handle 440? And we can, this is a really good problem. Like I love, it's a little complex at the end, but if we go here to Q norm and P norm, good. Wow. And then do 1 divided by that. Okay, so there is it one in, it's more than that. Super duper unlikely. Good to see you, Andy. So we should be going down to 440, and it's a bummer because the complexity of this problem is going to be lost by me doing the answer right here. We would clear it for this. Watch me get it wrong. And that's 6 standard deviations below the mean, right? So 60 times 6, 800 minus. It's cleared for that. The maximum shear strength would allow us that. Check answer. Boom. Yeah. Because we are saying with this that if your bridge requires a shear strength of 440, our rivets will work for you. Does that make sense? You're saying I need a strength of 440. So we are very certain we can meet that standard with these rivets. Like very next to none of them will fall outside. The curve does, I think this is good to illustrate, the curve does keep going. And so 440 would be down here. And it's very, 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 very unlikely that we would have a rivet at below 440. Does that make sense? So if they say we require a strength of 440, we'd say, yeah, I mean, our rivets are set for 800. There is some variation in them, but it's super duper unlikely that you will see a rivet that wouldn't work for you. I mean, anything's possible, but we'd probably catch it as we did like some sort of stress test on it to make sure it passes. So yeah, it's a good processing one, like Eastman Chemical and stuff. A lot of process control right there. SPC, statistical process control. It's just the complexity of it at the end. It should say, I wish it said something like, the company requires to certainty and wants to make sure they only market rivets to work at a strength 6 standard deviations below the mean, because that's all they're asking you to do is to go 6 standard deviations below the mean. And then, yeah, but so little confusing, but we're fine. I give that question a 7 out of 10. We got the Some IQ test question, but we need more questions after this. Here we go. Some IQ test. IQ test. So I'll go take an IQ test. Chapter 5, Quiz 1. We don't have any more questions after this. More questions, drop them in the chat. So we need more questions or we're done. Some IQ tests are standardized with a normal model of 96 and 12. So what are 96 and 12 respectively? 96 and 12 are the what and what of the curve. 96 and 12 are the what and what of the curve. I think it might be. What are 96 and 12? Now, if you remember, we do a lot of review right here. The mean and standard deviation, great job, Elaine, right there. And great job, Caitlin, too. And drop more questions because we're out of questions after this. So it's your call. This is the shape is normal. And then the center is 96, which is the mean. And then the spread is the standard deviation. Now, we have the apps pinned at the top of the chat right here. We'll type it again so Mubot can drop it. The apps right there. Thank you to Adam Spambar who made it. With the apps right here, you can go over here to the normal model. And you can actually put in the numbers. Now, I do suggest drawing it out, but it was 96 and 12, I believe. And then you can see the curve down here on what it would look like. Now, it doesn't show you the exact standard deviations, but you can get an idea. Where's that question? 96 and 12. So with this one right here, one of the things I have with standard deviations or z-scores is that something isn't unusual at 2 or at 3. Things are just more unusual the further they are away. It's not like I'm tall because I'm 6'10". I'm not 6'10". I would be tall if I was 6'9", 6'8", 6'7", 6'6", 6'5", 6'4", 6'3", 6'2", 6'1", 6 foot. As you can tell, it's kind of shades of gray. It's like, well, the further you are away from the mean, the more unusual you are. And it's just that you become more and more unusual the more extreme your z-score. So someone who is 5 standard deviations above the mean is super unusual. Someone who's 4 is very unusual. 3 is unusual. 2 is kind of unusual. 1 is high. It's not unusually high. So let's see what they say right here. Any IQ score more than 1 standard deviation of the mean or greater than this is unusually high? No. 1's meh. 2 is kind of high. Any IQ score more than 3 standard deviations? Okay, so now we're getting to the iffy stuff. Okay. Any IQ score more than 2 standard deviations above the mean or greater than this is unusually high. One would expect to see an IQ score 3 standard deviations above the mean or greater than only rarely. That sounds right. Because, okay. So you see how this one down here talks about 3 being unusually high. And then this one says only rarely for 1 standard deviation. Say, hey, what's up, Hayden, right here? 50 points, Hayden, in the chat. Good seeing you last night. So what they're trying to communicate right here is 2 is unusual and 3 is super rare. That's what they're trying to communicate is 2 is an outlier and 3 is very much an outlier. Yeah, Jamarcus, put him in the chat. We'll do him here next. You got it. We don't have any questions after this. So we just go 96. It's going to be 120. 96 plus 2 standard deviations, 120. And then we add another standard deviation to this, which is 12. That's 132. And that should be right there. There we go. Once again, the wording on this makes it clear that if you read this right here, 3 is unusually high, but then they say 1 is rarely. 1 would not be rarely. What % of the time would we see someone with an IQ higher than 1 standard deviation above the mean? What % of the time would we see someone with an IQ, and this is not IQs on here, but I could draw the IQ numbers. What % of the time would we expect to see someone with an IQ more than 1 standard deviation above the mean? What % if these are the IQ numbers, I'm using similar numbers. What % of the time would you expect to see someone with an IQ greater than 1 standard deviation above the mean? So, and this is why, 16%. So does that sound like a rare event? If I tell you 16% of the time something occurs, does that sound rare? Would you say that's rare? If I tell you 16% of this box of chocolate is white chocolate, you'd be like, ooh, they're rare. I'd say they're uncommon, but I wouldn't say rare. Like if I say I got a rare Pokemon, then people wouldn't say it's a 16% probability. You'd probably say it's just like one of the lesser common Pokemon, less common. I wouldn't say rare. The extreme outlier is an electric car. Oh, okay. The boxplot shows. Let's do those. We got some chapter 4 coming up, but drop more chapter 5 in the chat right there. All right, we're gonna do some chapter 4. Got the box plot, the extreme outlier. Thank you so much, Jamarcus, right there. Let's save this so we don't lose it. Hey, we're gonna do some chapter 4, but drop your questions in the chat. Remember, We do what people ask. If you're here, you get to ask the questions. Jamarcus, Caitlin, and Lane, and Hayden, good to see you here. Assignment manager, more coffee. Okay. The box plot and the extreme outlier. All right, here we go. We got the box plot. The box plot. Okay, let's do the box plot. Here we go. The box plot shows fuel economy ratings for 67 compact cars, and then there's an electric car on there. So when you look at this right here, we need to know what a box plot shows us. What kind of data does a box plot show us? What kind of data does a box plot show us? That's my first question that we should all know the answer to. What kind of data does a box plot show us? The answer is on the screen. What kind of data does a box plot show us? It's in the top left corner over there. You could say two things about a box plot. A box plot shows us what kind of data? What kind of data does a box plot show us? What kind of data does a box plot show us? Oh, wait here a moment. Quantitative, and it's going to show us univariate quantitative, right? So it shows us univariate quantitative data. And then we could do what are called side-by-side box plots. So I'm going to go right here and add a little bit more to this. That's a box plot of the height of students. And we could go right here and go x equals gender. And we could get side-by-side box plots. And what I really like is I could just color them in. And there you go. There are side-by-side. Let's go to Phil. I prefer Phil better. And there are side-by-side box plots showing the heights of males and females. A singular box plot is univariate quantitative. Height is quantitative. So you can see the heights of students. And then side-by-side box plots are going to be bivariate because the x is categorical. So make sure to know on the screen right here when you see side-by-side box plots down here, it's a categorical x, and box plots can be used to show multiple distributions. Box plots are great for doing that. It's for Canvas content. A singular box plot, not plural, is just to show one quantitative variable, univariate. And that's what the graphics up here are, univariate, and the ones in here are the bivariate displays. Okay, so that's what we got going on right there. And we have our question showing us a box plot right here. Now, what's very important to note is there's 67 observations. They've got the notation for sample size. And then we need to start connecting the dots. Because the min, which is part of the 5-number summary, is there. The Q1 is here. The median is the line right there. The Q3 is there. And the max is over here. So we've got the 5-number summary right there. The standard deviation and the mean are given. You don't see those inside of a box plot. Jump actually shows the mean, but not traditionally will you see the mean inside of a box plot. So with this information on the screen, what can we do? Let's find out what the question asks. If we remove the electric car, how will this affect the standard deviation? Now, the formula for standard deviation is going to be like squared distances from the mean summed together and averaged. So do I have the notes still up for it? Chapter 2, we do. We have the notes for standard deviation. So the standard deviation formula is right here. And if you look, we have the standard deviation. And that's actually, I should have said square rooted because squared is variance. So you are taking an observation's difference from the mean, and then you are squaring it because you don't care if it's positive or negative. You're summing them together, and you're dividing by n-1 for sample standard deviation. Standard deviation as a population would just be n right here, and that would actually be sigma. So just real quick note, kind of technical stuff here. If you had this formula right here, and you used the true mean, then you would have sigma right there. So that is population standard deviation right there. And I guess we got to be really technical because at that point, that would be mu. Oops, where's my drawing? I'm going to put that as mu. So it is the observation minus the mean, the squared difference, each observation. And we need to do the sum of the ith observation right there. So it's a little bit complicated, but think about this. When is standard deviation larger? when observations are what? When will standard deviation increase? This is the key stuff to know. Standard deviation will get larger when observations are what? The answer is within the problem. And so look at the notation right here, Jamarcus, and standard deviation gets larger when observations are what are from the what. So standard deviation gets larger when observations are what are from the what. When is standard further from the mean, right? So that's how this increases. We don't have to solve this by hand. We just have to understand that standard deviation is kind of a metric of how far things are away from the mean. So if we remove this point, that removes away points that are far away from the mean. So what would that do? The standard deviation would be lower, since the standard deviation is calculated by summing the squared differences, and that's it right there. Standard deviation is calculated by summing the data values? No. It's calculated by summing the squared differences. We don't make you know it. That's super technical, but you can see it in the notes right here. It's summing the squared distances and then averaging them together. It's an average squared distance. And the mean, removing the electric current will drastically decrease the sum. As it says, drastically decrease the sum. And you could see that in the equation right here, the sum of the squared distances of the observations from the mean. So the sum of the squared distances from the observation from the mean, we square root it to take it out of squared units, and then we divide it by n to make it an average right there. Kind of technical, and it wouldn't be greater. How will this affect the IQR? So think about how the IQR works right here. The IQR is based on a distance two points are away from each other. So if we put a bunch of numbers right here, like 0, 1, 1, 2, 3, 4, 5, and then we put 100, the IQR is probably somewhere in here. So what is the value of the IQR currently? What is the value of the IQR currently? What is the value of the IQR currently? Like, that's probably about where the IQR is at. Yeah, I think might actually be it. I could check it, but that's a pretty good guesstimate of the IQR. So the IQR, if we go here and do the min, Q1, median's going to be here, and that's Q3, and that's the max. Actually, I think that is correct. So what is the value of the IQR? The IQR is the range of the middle 50%. What is the value of the IQR? 1, 1, 2, 3, 4, 5, 100. You're right. Oh, really? Well, according to this, it's 3.25. So once again, we don't have to find these values ourselves, but what happens if I remove 100? So you can see here visually, here we'll show it on 2 lines of code, but watch, whoops. If we go ahead and remove 100, do you think the IQR will change drastically? So now the IQR is probably somewhere in here-ish. Do you think the IQR drastically changes, yes or no? If I remove 100, do you think the IQR drastically changes? So if we go in here and we remove 100, and now 5 would be the max, do you think there's going to be a drastic change to the IQR? I mean, the numbers are going to shift a little bit. Probably not, because it's still based on just positions right here. So if you look at the IQ here, it's 2.5. Now, there was a little bit of a change, but once again, removing the max or the min is usually not going to change the positions too much, because what we're doing right here is we're deleting just the highest point. So in our original data, we're just deleting this point right here, and these other distances right here are probably going to stay about the same distance away. It's going to shift the data over a little bit, but the IQR is used with what other value? The IQR is the measure of spread, and we use that with the center of what? The center, oops, I highlighted the wrong value right there. There we go. What center do we use with IQR? The center with IQR is what? And this is for skewed or data or with outlier data. The center would be the what for the median. Yep. And we use both of these together because they're not so much impacted by outliers. That's why they're paired together versus over here, you have the mean and standard deviation, which are paired together for normal data. So if you have outliers, they're not going to impact the IQR much, and they would impact the standard deviation. Like if we go here and run standard deviation on this data, the standard deviation is 34, but then when you remove the outlier, the standard deviation is, do you see the big impact right here? So let's call this data 1. So check out the differences in standard deviations for both these data sets with the outlier removed. So the original standard deviation is 34. Let me change my options digits. I did that yesterday to help out. Digits, 7. There we go. There's the standard deviation there. And there's the, so you see the big change to standard deviation. Standard deviation is drastically different because standard deviation is very much impacted by outliers. And that's what they're trying to show you with this. The ICAR would not change much. That's all we got to say. And then you can read the rest of their answer. Although removing the electric car does possibly change the location of each quartile. Yeah, which is exactly what we were talking about. It's not going to really impact the IQR. It could change the locations of the quartiles. Does that make sense, Jamarcus? And once again, we're going for that deeper understanding because we're kind of showing how to do the problem or the answers, but seeing how the standard deviation by removing an outlier changes from with the outlier of it's 34, and then without the outlier, it's only 1.8, whereas the IQR with the outlier is 3.25, and without the outlier is 2.5. So if you compare these numbers right here, here is the change to standard deviation. You can see there's this way different numbers. And then the IQRs, although they're a little different, small differences right there. The Research Institute Innovative Technology, you got it. Let's do it. A little congested today. No. We got the extreme outlier. Okay. Let's go check. Okay. Got a research institute right here. Let's check out this problem. And 43, 44. Step tool 1, chapter 4 quiz. Okay, let's check it out. Is there any help me with the question? Yeah, what's it say, Courtney? Let me know. Everyone gets different questions. Let me know, and we'll take a look. Yeah? Okay, so we got load times of domestic. So we got different years right here. This goes from like 2002, 2003, 2004, 2005. Outlier there in 2015. Side-by-side box plots showing categorical X, quantitative Y. Although year is kind of quantitative, they're using it to group it. So you could do that with year. Just group it by year. So which of these load factors were generally more variable in the 2000s, but become higher and less variable each year? That might be true. They do. If you notice, the IQRs get smaller. No, they weren't lower. Yeah, wait, they were lower. The variability load factors did not increase. Load factor was generally lower and less variable in 2000, but become higher and more variable. No. Here are box plots. Okay. Is that chapter 4 you said? Canvas count number 3? Yeah, we can do that soon here. The load factors were generally higher and more variable. No, they weren't higher. Okay, so they need to be lower. Become higher and more variable. I think they become less. They become less variable. You can see the IQRs are getting smaller. So load factors were generally lower and more variable. More variation. And there we go. That should be it. Yay. Chapter 4, you got it. And here are box plots. The points. Yep. I think we have one more for Jamarcus right here. And the extreme outlier Jamarcus has right here. Let's check out the extreme outlier one. Hero box plots. Well, we found the hero box plots. So let's do this one. And then let me mark canvas content number 3. So here we go with some box plots right here. And we have 2 box plots. Summarize the similarities and differences. So what is similar between these box plots is box plots right here. What is similar between these box plots? So don't look at their answers. What is similar? The medians, yep. And then we see vast differences between the spreads. So the centers are the same, but the IQRs are very different. IQR right here, much larger for Holly, and Sue, a much smaller IQR. Her min and max is also lower, so the ranges are different. Both players have approximately the same median, but Holly has a larger IQR. That does look right. Well, they don't have the same right there. They don't have the same IQR. That's different. Choose the best answer. Okay, the coach can only take one player to the state championship. Which one should they take? Well, they both have the same average. Depends on the preference, because maybe, you know, Holly has a higher potential, but Sue is more consistent. So it really depends on what they want. Do they want, you're welcome, Jamarcus. Do they want someone who could get really great points, or someone who's really consistent? So if you're at the end of the game and need points, you'd put Holly in. If you want someone throughout the game who needs to be consistent, you'd put Sue in. First Officer Harrison, good to see you here. Drop some questions in the chat. But yeah, we've got another extreme outlier one. So that was a good one right there. Let's see right here. You're welcome, Courtney. Did we find the extreme outlier one? Extreme outlier. Maybe we did it. I don't see it. Might have been the start of the other question. Oh, hey, we got canvas content number 3. Let's go do that. Here we go. Canvas content number 3. Let's go take a look. Canvas content number 3. Chapter 5, a good one right here. Let's do a few versions of it. You ready, Sloan? We're going to do a few versions of this. Tool 1. There we go. Let's check it out. There we go. Okay, so here we are with Canvas content number 3. And let's do it. Okay. And these problems are very specific on the test. They tell you to use the 68, 95, 99.7 rule. What is the first thing you should do if you see data right here? What do you need to do with this data? We practiced this a lot for this chapter, and I think a lot of people don't do it. And I'm like, no, if you don't do this, you could get it wrong. What should you do immediately with this data? Once you get this question like this, what should you be doing to practice and on the test to make sure you get it right? We'll look at it. So what do? We always draw it out, then draw it out. Yep. So we're going to do 2 parts to this drawing. We're going to go right here. Now we know that it is normally distributed with a mean of 25 and a standard deviation of 3. This is the shape. This is the center. And this is the spread of it. Shape, center, spread. Shape is normal. Center is 25. And standard deviation is 3, which is the units you go up and down each time. So when we go right here and put in these numbers, we're going to go up and down 3 each time. So that's 28, 31, 34. And we go down, down, down. And this is 22, 19, and 16. Now, always below it, I put the z-scores right here with 0, 1, 2, 3, -1, -2, -3. So with this, what do we see? Well, it asks about someone who is at 31 minutes. And it says above 31 minutes. So we have to shade in the curve going above 31 minutes. Do you know what the answer is, Sloan? So this requires using the 68, 95, 99.7 rule, which is given to you on the test. And to do that, we would go plus or minus 2 standard deviations and put 95% right here. So 95 is for the second standard deviation. This is for the first. This is for the third. And so what would be the answer right there? A good drawing can kind of help you get the right answer, but Sloan, what would it be? Because if 95% is on the inside, we can figure what's on the outside. Well, 5% is on the outside. Yep, you might be following along right here. 5% is total on the outside. So 5% is total on the outside. Then that'd be 2.5 on either side. So 2.5% on either side when we cut the 5% in half because it's symmetric right here. So it's going to be 2.5. Good question right there. Definitely looks a lot like the test. So we have right here, you decide to buy a candy box that has a weight of this. Calculate the z-score. So a z-score is a standardized difference something is away from the mean. So to find a z-score, we have to figure out how many standard deviations something is above or below the mean. So knowing your notation is going to be key right here. If this is the candy box weights, that's y equals, which tell us this is what we observe the candy weighing. This is the standard deviation right here, which is going to be sigma, and this is going to be the average weight, which is going to be mu. So now all we have to do is plug into the formula of observation minus mean, which is a distance, over the standard deviation is equal to the z-score, which is how many standard deviations something is above or below the mean. So now plugging in the numbers right here, we get 476 minus 457 over 21.1. We solve through. It was 19, right? There we go. So that's 0.9. 0.9. What does this 0.9 mean? So let's do our drawing real quick. What does 0.9 mean? What does so Sloan, what does 0.9 mean? Because if we go here and go one standard deviation above, one standard deviation above is 478.1, and we landed right here with our y observation. That's y equals 476, which is a z-score of 0.9. So what does that mean, Sloan? That the z-score for this observation has a z-score of 0.9. What does that mean? Like, what would we say about that? How does that interpret? The observation, 0.9 watts. You're right, 0.9 above the mean, but 0.9 what? Here's a hint on the screen. .9 what? It's 0.9 standard deviations of the mean, and you could find out the answer the same way by going right here and taking the standard deviation and doing times 0.9, and then add that to the mean of 457, and you get the observation. Just round it to 476. So we can confirm the answer right there and check our work with the following. Good deal. And so the answer is 0.9. A test is given to students with a mean of 70 as standard deviation of 2. Jerry scores a 70. What is his z-score? So this question right here, we got a really easy version of it. What would his z-score be? His z-score would be what and why? What would his z-score be and why? What would his z-score be? So he scored So we got a very easy version of this because Jerry scored where? Jerry's score is the mean, so he's not above or below. He has a z-score of 0. He's right at the mean. So you would say he scored the mean. This is where it gets a little more difficult, I would say, but we just need to know how to read the applet pictures, and we need to be able to draw on them. So let's go ahead and do that. So with this right here, we have the body temperature of individuals, and this graphic is currently showing us what down below? What is the graphic showing us at the bottom of the screen? At the bottom of the screen, we are seeing what's. What are these values right here? Are those body temperatures? So we have to know what we are seeing. It says this is on a curve with a mean of 0 and a standard deviation of 1. So what are those values on the bottom of the curve? Because it says it has a mean of 0 and a standard deviation of 1. All of those are what's. What are those values on the curve? Every value on this is called the standard normal curve. And everything on the standard normal curve is a what? A good answer if you don't know is I don't know, but feel free to answer. So we have to know what are those values on the normal curve down there. On the standard normal curve, everything on it is a z-score. Those are all z-scores. Standard, pretty much, well, they're z-scores. And remember, whenever we draw the curve, we always draw the curve with the z-scores down below it. So you'll see me put the z-scores, and you'll see me put the context of the question. So we need to put the context of the question below, which is going to help us solve this problem. So 98.2, and then we need to go up by this right here, 0.7. And we might be good because what this question asks us only requires us to go up and down one standard deviation. So it says, what body temperature is the 80th percentile? And this is where it's like, okay, what are you asking for? What percent of area is shaded on the curve right here? What percent of area, Sloan, is shaded on the curve in that black area right there? What percent of area is that? What percent is that? Well, it's close to 68, but what exactly is it? So take a look on the second line or the second group right there. What exactly? Like, it's exactly this percent. If we had to say an exact percent of it, we'd say it's exactly this according to the question. It's exactly how much? It's about 68, but it's exactly how much? It's going to be exactly 60%. That is obtained right here, where it says the middle 60% is shaded. If 60% is in the middle, what is total outside? What is total outside? So if 60% is in the middle, what is total outside? You got it. Great job, Sloan, right there. Some points. We haven't hit points in a while. Let's hit, we'll hit a few more point buttons. So 20% is above. Now, if we are looking for the 80th percentile, why is this mark right here where the 80th percentile is at? Why is that spot right there where the 80th percentile is at? So why would this arrow point to where the 80th percentile is at? So you have to know what the 80th percentile is and then understand why that spot is pointing to the 80th percentile. So why is that spot the 80th percentile? Percentiles tell us how much data is below a certain point on the curve. So below that point is 80% of the data. And you got it right there, Sloan. That is correct. So do you have a guess of the body temperature of the 80th percentile? Do you just take a guess? And I want you to just guess, and then we're going to find the answer. Remember, this is body temperatures. Do you have a guess? Hey, RotoWave, good to see you here. RotoWave. Do you have a guess of the 80th percentile of body temperatures? Just a guess. Remember, it's body temperatures. Do you have a guess? We are looking for the point there. Do you have a guess? Just a guess right now. Let's see. What would be your guess of it? Good guess. I think it's a little higher, but that's a decent guess. So it's going to be closer to 98.9 than it is to 98.2. And so here's the thing. What do we know of the 80th percentile right now? What do we know of the 80th percentile? We know the what of the 80th percentile right now. What's that number I highlighted and what does that mean? We know the what of the 80th percentile. What do we know of the 80th percentile? It's z-score, yep. That's the z-score of the 80th percentile. So how could we use that to find the answer? So if we know the z-score of the 80th percentile, how could we use that to find the answer? Because what does the z-score tell us? Like if I told you the z-score for the 80th percentile was 1, what would be the body temperature? Like if I said the z-score was equal to 1, what would be the body temperature? If I said the z-score was equal to 1, just use that. I would then say, what is the body temperature? If I were to say the z-score is equal to 1, you'd say, oh, the body temperature is this. Great job, Sloan. That's what it is. And so can we use that to bring it into a formula and say the observation is equal to the mean plus the z-score times the standard deviation, because that's how many standard deviations something is above or below the mean. And then just take right here and solve. I think it's like 98.8. We'll check the math here in a moment. Is equal to the mean of 98.2 given above plus the 0.842 times this is the z-score times the standard deviation of 0.7. So there we go. The mean plus the z-score times the standard deviation. The numbers are given right there. 0.842 times 0.7. There's that. And then we add that to 98.2. And that rounds to 98.8. Does that make sense, Sloan, right there? How are you doing on this? RotoWave, good to see you too. Does this make sense? The z-score tells us how many standard deviations something is above or below the mean. Where did the 0.7 come from? Good question. Where did it come from? Take a look up there. How'd I know to use 0.7 and why? Where did the 0.7 come from? Really good question. If you don't know, feel free to say I don't know, but where did I get 0.7 from? Where did 0.7 come from? I see. Yep. Good job. That's what I wanted you to see. Yeah, I can say it, but then I want you to see it. It's more important if you see it and you say, okay, that was the mean and standard deviation, 98.2 and 0.7. So the 0.7 was the standard deviation. That's also how I knew the distances on the graphic right here to go up and down 0.7. When I drew this out right here, I went up and down 0.7 right there. Good stuff. Good stuff. So 98.8. These questions are really good practice. These are some of the tougher questions on the test for people when we give you a graphic and we ask you to solve. So to one decimal, I think we got it. Similar question right here, but this one's using the 68, 95, 99.7 rule. Below 22 minutes. Any ideas on this one? I think we have a drawing that can work. Did we do it with 25 minutes at the center? There it is. And it wants below 22 minutes. So below 22 minutes, what would that be? See if you can solve it while I'm doing the drawing. Still the same thing right there. So let's bring that back. Below 22 minutes. Does anybody know the answer? Well, no, this one is, so below 22 minutes is down here. So below 22 minutes would happen about what percent of the time? Below 22 minutes would happen about what percent of the time? So the drawing should help out right here. So if 68% is on the inside, and have your pictures. Take pictures of the work we have over here. This drawing right here that we have up. Other drawings we have 16%. Great job, RotoWave. These questions really come down to practice and drawing the curve and knowing how to break down the curve into the percentages. We showed pictures a little while ago on how to break down the curve, but we've been drawing a lot today and just knowing how to draw the curve, the percentages on the curve. We did it in class, so drawing it with us in class, best way to practice, and you should be able to draw these out. Because a lot of the questions, although they seem difficult, we're going to do a speed run of this now. We should get 10 out of 10. If you understand what they're asking, then the questions are not so bad. This is the one we got earlier, so that's 98.8. We just add, because we know the z-score, so if we were to actually solve this, it would be 0.842 times 0.7 plus 98.2. There's the answer. And then this one right here is a little bit similar. It's asking right here, what percent would be above, higher than 99.26? Well, the graphic is showing us that the shaded region is 13%. So it's saying that this right here is 13%. So if it wants above 99 point, if it wants this, that's 6.5% because it's half of it. So that's just cutting it in half right there. So it says above, yep. So 6.5, enter in as percent. That's that. How does the normal probability plot determine if distribution is normal? This is if it follows the straight line. We did a lot of things yesterday with this. So if something is normal, the normal probability plot will follow the straight line. Oops, thought I clicked that. Oops, didn't do that. This is not normal, so it's going to look bent right here. We go to the normal probability plot, and it's got a bend to it. Definitely check out the notes from yesterday where we go over it looks normal, and we went over the 3 ways to determine, and they're all listed right here. 1, look at it. 2, does the normal probability plot follow the line or not follow the line? And 3, does the goodness of fit test have a p-value higher, greater than or equal to 0.05, or less than or equal to 0.05? And so we have the same sort of knowledge right here. It determines if it's normal by it follows a straight line. That's right there. We have above 31 minutes. That's 2 standard deviations, 2.5. Test is given. Jerry scores this right here. What is Jerry's z-score? That should be 1 1/6. A 6 is, so I'm going to guess this one. A 6 is equal to, is that a 6? 2 decimals. So I'm going to round. I don't want to mess it up. I was right. We should have it. We did it. What are you thinking, Sloan, right here? That is me. I had yeah, good job, Sloan. How does normal probability plot determine? The line follows a straight line. Standard deviation 1, Jerry scores that. He got the mean. Right here, we got the same one we've had a lot of times, 98.8. 31 minutes above, so 2.5 because it's a z-score of 2. This one we have to actually work because the candy box weighs that. So it weighs 496 minus 479, the mean, divided by the standard deviation. And there it is right there, 2 decimals. It's got to have a give on it, right? That's right. Is that it? And this is where you want to be at with these quizzes. Can we go back to ones? The each side? Is it this one right here? Are you asking about, is it this one right here, Sloan? Yes. Okay, so what is this showing us? It's shading the inside, outside, above, or below. What is this shading for us right here? Inside, outside, above, or below. Inside, outside, above, or below. What is it shading? Is it shading the inside, outside, the outside, right? Okay, so here's what we can do to actually, do it even better. Is we can go to the apps. And now you can't do this on the test. These pictures give you enough information, but we're learning and we're practicing right now. So we're going to go to the apps right here. Thank you to Adam Spanbauer once again who made these. The app's going to show up. It's pinned at the top of the chat right now, so I'm going to pull it up via the pinned message. Where's the apps? Mubot, where you at? So Mubot, throw some points to them. And sure, there we go. Mubot does not want to talk to us today. Okay, so here's the apps. And the question said a mean of 98.2. That changes the center. And a standard deviation of 0.7. Now we can cheat and get the answer. We got to be careful because this is Mubot is sleepy. He's saying I'm Mubot. What happened to our apps? I don't know. Maybe it's because it's pinned. It wants above 99.26, so we can cheat. And I think this will help you see how the answer works for this, because if you go to above, we need to actually change this to here and go above. And let's do a few more decimals on it. There's the answer. Now, let's think about why this is the answer. So we're going to put both of these on the screen at the same time. 2 seconds here. Let me get them both on the screen. Okay. So I want you to think why the answer is 6.5. What percent of area is shaded right here? On this graphic, on the outside is how much shaded. On the outside right now, on this graphic right here, how much is shaded? It makes it smaller when I do that. Now it makes it bigger. Perfect. How much is shaded on this curve? 13%. So that means total shaded is 13%. So how in the world, if this is where 99.26 is at, you see that's where it's saying that it's shaded outside of these numbers, and then we want above 99.26, how in the world did we get the answer of 6.5%? Which we are able to obtain. Do I still have, I don't have this drawing up here, but if we know 13% is total outside, and then you look at these areas right here, how are we getting 6.5% for that area right there? It's just learning. Yep. And then once again, you don't have to use the applet because you just know that it's symmetric. You can then, and the applet would find you the answer, but that's why people will say, and let them know, look at the Canvas content, look at how the we ask it, and you will be able to solve it without the applet. So the applet would get you the answer, but also you are able to solve it without the applet. So really good questions right there. Good practice. He got a 79. Oh, I did really well. There we go, right there. And this one right here is down. And this one. Yeah, great job. I think we did it right. It's one standard deviation below the mean. Oh, one unanswered. Which one did I skip? This one? Oh, 6.5. Awesome. Well, good work. I might take a short break right here and relax for a little. Can the apps do the last one as well? Yeah, well, the apps can do all of them. Well, no, this one uses the empirical rule, so you'd have to watch out using the app for this. Do not use the apps for these types of questions because it says, you see how this is like bolded and highlighted? What do you think will happen if you use, you see how it has no margin of error? You have to use the empirical rules. Does that make sense? So the app will get you the exact answer, but this is why this is like bolded and highlighted, and people will message me and say, but I use the app, and it says it's like we bold and highlight this for a reason. So it's literally saying do this. The app will get you close to the right answer. I think it'll be like 15.86. If I had to say exactly, I think it's 15.86. We could go check. Once again, don't use the app for this question because it uses the empirical rule, which is numbers we can always use. So standard deviation is 3, below 22. And if I carry the next decimal, I was wrong. I was wrong by 1 decimal. I said 15.86. It's 15.87 because it's basically 16%. But notice there is no leeway on this question because it's using the empirical rule. And the empirical rule is going to show you below 1 standard deviation is 16%. That's not the empirical one. Where's our empirical rule version? There it is. So below is 16%. Good. Well, so the app is very exact. It does the exact percentages, but it's basically 16%. But that's why there's always more decimals, but the app can get you ridiculous decimals. So if you put it to 2 decimals, you would get it correct. But if you carry extra decimals right here, you would get it wrong. Reason being is because inside of plus or minus 1 standard deviation is going to be 68, and thus outside, and that's the empirical rule number, is 90, or outside is 32. But when you look at this exactly, it's 68.26, I think. There it is, there it is, 26, so 279. But there's more decimals. The next one is 95.449. So go here and go plus or minus 2, 95.449. And there it is right there. And then next one's 99.73. This is the more decimals. But we like to say 68, 95, 99.7. So here we go right here. Wait. -1, 1. -2, 2. -3, 3. Okay. So here we go. 68, 95, 99.7, but all the decimals, right? There we go. So now 68, 98.3, 95.4, 99.7, 3. Does that make sense, Sloan? There's more decimals, but when we do the empirical roll, we do 68, 95, 99.7. And then it literally gives you those numbers. It's just we're not carrying every decimal because you'd always carry more. So the reason the app gives you slightly different answers is because you can just get every decimal further out. So when you look at like the 68%, it's not exactly 68, it's 68.26. But for all intents and purposes, we just say 68. I mean, 68.3 though, if you want. But be more to memorize. It's just easier to say 68, 95, 99.7. Well, good work right there. Excellent job. I'm going to take a quick break right here on this Valentine's Day. Hope everyone's having a great Valentine's Day. We'll be back here in a little bit. Yeah, you're welcome. We got a lot of work done this morning. Let me go save everything in the video right here. A lot of Canvas content and really good practice and review. Awesome. I will see everyone later. Bye for now. Bye.